This is really early on within the lecture slides. It's officially in play posit. So we had 4 kind of problems here. I honestly don't remember. I meant to go back and look, and I forgot if all of those were actually explained in the play posit or not.
None of them.
None of them were. Okay, even better. Cool. So, for me personally, looking at these 4, it was horribly designed from an instructional standpoint because the top one is the hardest, which is probably the one that everybody would start with, and the bottom one is the easiest. So let's start at the bottom and go up. Okay? So which compound would we predict to have the highest melting point? So first and foremost, if we're looking at melting point, what we're talking about is our phase changes. Okay? And phase changes are dictated based off of intermolecular forces. The intermolecular forces ultimately come from our bonds. So when we look at an individual question, that question is going to provide us a Lewis structure sometimes, a formula other times. In this case, it's just formulas. And what you're supposed to do is interpret that drawing to say these are the bonds present. Once you know the bonds that are present, you can then predict the intermolecular forces. Once you know the intermolecular forces, you can then rank them or apply the intermolecular forces to that particular scenario. If we're looking at our phase changes, as we transition from a solid to a liquid, what is happening on a molecular level? So there's a solid, and if we transition to a liquid,
Bonds are breaking.
not quite.
I tried.
It's not a bad try, and it's a very common answer, and some people would actually accept it. I don't accept it because I think it's a false usage of the word. If we're saying a bond breaks, what you're saying is that circle is no longer a circle. If a bond breaks, I'm breaking the carbon-carbon connection. Each of these circles represents a single one of those molecules. Okay? So if you're saying a bond, you're breaking something internally within the molecule, and that is not true when we're looking at phase transitions. This is why when we boil water, what do we get? We get gaseous water. We don't get hydrogen and oxygen gas. Because if we did and we lit a match, like, poof, that would be very problematic. Okay? So lighting a match over boiling water isn't a big deal. Lighting a match over water that has broken bonds is very problematic.
The molecules are dispersing.
Okay? What's preventing them from dispersing in the first place?
They're packed pretty close together.
Why are they packed close together?
Because they're cold and there's not a lot of energy.
What is that energy doing? Because you're absolutely right, but it's addressing what's happening at each of those stages. When you slowly increase that energy, because I can take cold water and I could take cold carbon dioxide. If I go to -5, cold water is a solid. Carbon dioxide is not. It's still a gas. So it's not just that it's cold, because different materials still have different phases at the exact same temperature. What's different between those?
Energy levels?
What energy levels? And that starts to get kind of subatomic, and I don't think you want to go that direction.
Anybody want to jump in? I'm really trying here.
Because I think the whole play posit was based on it.
Which play posit? Forces.
Forces. Yeah. It's not bonds, it's forces. Bonds are the sharing of electrons between atoms. Forces are not the sharing of electrons. It's how those individual molecules contact each other and talk to each other. Okay? If that force is really, really, really strong, what does that mean at an individual energy? Well, it's still there. What happens as I add more energy? It eventually vibrates the molecule so much that what happens to that interaction? It's no longer present. And now we've transitioned to phase. So when we're looking at this transition from solid to liquid to gas, what we're doing is breaking the forces that attract the molecules. Okay? The liquid to gas phase or transition is a little bit more challenging, but that's probably the most extreme. When we get all the way up to the gas, we have formally broken all forces. They do not exist anymore. Okay? Our particles do not talk to each other. When we're at a solid, they're talking as maximally as possible. Right? And so what we want to be able to do is to look at a formula and say, this is the interaction that it's going to produce somewhere else. Which makes me suggest that we should try to backtrack on this. So let's backtrack up to this interaction. Okay, and we'll simplify some of this out. If I take a look at sodium chloride, okay, I know the font's weird, it's stupid copy-paste stuff. Okay, a single molecule of sodium chloride. Right? And for those people that care about calling it molecules, piss off. We're calling it a molecule. Okay? That molecule needs to interact with another molecule. Okay? So the question becomes, how does it interact? Does it interact like the top scenario or the bottom scenario? What? That was an awful fast answer. Why does it interact like the top scenario?
Because of the charges.
The charges align. What we're trying to do is neutralize those charges. So when we look at sodium chloride and we see how it stacks and interacts, it generates this formula. It's that repeating unit, positive, negative, positive, negative. That's how it builds. Guess what happens when you move to a different molecule? The exact same thing. Does it always? Right? Why are we getting positives and negatives here? Why is sodium positive and the chloride negative?
Because of the way the electrons are spaced around the molecule.
The way the electrons in that bond, because it's really the only bond that we can reference for that molecule, are spaced around where they're being located. Looking at the periodic table may not have been a bad idea, just for the record. Okay, we'll see where that goes. What dictates how those electrons are spaced around that bond?
Valence electrons?
Nope.
Attraction?
Why should the electrons go to the chlorine and not the sodium?
Because it's more electronegative.
Electronegativity is what dictates where our electrons move, how they're moving through our molecule. They're one of the things that contribute, okay, at a largest scale that we want to look at, still very, very small. Okay? So when we're looking at that ionic compound, we're saying the electrons have formally moved over to the chloride. That's why the chloride is negative and the sodium is positive. Okay? This hits a weird gray area. If the electrons have formally moved over to the chlorine, do you have a bond? Well, no, because bonds are talking about sharing of electrons. Okay? So our ionic systems straddle a strange gray area. If we call this a molecule, then we can reference the connection that brings them together, a bond, and we would define that bond as an ionic bond. Okay? If we now bring in a second molecule, okay, either in purple, well, that was supposed to be a purple underline, okay, or in blue, we're now looking at a new interaction. How does that thing interact? Okay. Well, is it the same molecule?
Yeah.
Is this box the same as this box?
Yeah.
It's an interesting statement. So what you're saying is that when I look at the interaction between two people, they become the same? No? Well, this is two people. I have a red person and a purple person, and I bring them together to interact. And what you just told me is they're the same. So they are now one person?
No.
So they are the same kind of representation, so we could, this is going to turn for political, but I'm not trying to make it that way. Female and female, okay? We're now looking at two females interacting, okay? They aren't the same thing just because they're both females, okay? They're a different unit of that. So when I now look at that interaction between them, We're interacting two different molecules that have the same character, if you will. Does that kind of make sense?
Yeah.
Okay. Why does that become important to us? Well, if we're referencing the connection within as a bond, how do we reference then that interaction, that dotted line?
Of course.
That's now not a bond, because we aren't connecting them per se, but there's an attraction there. Okay? That attraction we'll define as a force. Well, is that different for an ionic system? Okay, and perhaps this might be the issue you guys were looking at. If we say sodium and chloride, and then we put sodium and chloride, what is the difference in interaction here versus the difference in interaction over here? Versus the difference in interaction over here. Whoops. We were like, it's minuscule because it's positive, negative, positive, negative. And that becomes, I would argue, the issue with our ionic bonds. Ionic bonds change kind of the format. They aren't actually sharing electrons. Well, a bond is sharing of electrons. So I can't really call them a bond. Okay? So I should really call them a force. But if I'm calling them a force, now I'm breaking interactions and it becomes this weird gray area. So what happens if we switch to a different system? Let's take a look at, let's not do that one. Let's do this one. Okay? We're going to get a similar system. Call it purple and blue. What is happening in that connection?
Polar bond.
Okay? It's a bond. How do I know it's a bond?
Because they're sharing electrons.
How do I know they're sharing electrons?
Because it's a bond.
What about that drawing makes you go, that is a bond?
The line.
It's a line, thank you. Okay, it doesn't have to be hard. Okay, we're showing a line. That line represents a bond. Okay? Is that bond the same bond as over here?
No.
Ooh, why not?
One's ionic and one's polar.
How do you know one is ionic?
Because you wrote ionic under it. And it's also metal. Too.
Ah, there we go. Fixing your answer, thank you. Okay? We know that an ionic bond is a metal and a non-metal. And if we go through and look at our other example for our bond, those are both non-metals. I'm going to want this one. Okay, two non-metals. So it's a different type of bond. One is ionic and one is some other type of bond. In this different type of bond, what happens? Well, they're sharing electrons. How do I know they're sharing electrons? We're seeing that line. Okay, so cool. What does that mean for us? Okay, well, what happens out here? We've got the purple dash versus the blue dash. What are we referencing there? Which interaction is more likely?
The top one.
Why the top one?
Because, once again, that would be positive to negative.
What positive and negatives? I don't see any positives and negatives.
I see them in my head.
Ah, awesome. So what we're now starting to do is propagate out those differences in electronegativity into our head to apply what that means as an overlay over our structure. That becomes important. Except nobody can see inside your head, so what should we do? We should draw them out. Because oxygen is more electronegative than the hydrogen, we would expect the oxygen to carry a negative and the hydrogen to carry a positive. Oxygen should be sucking those electrons away. But when we draw it in that notation, what does that start to look like?
Different than the other one you wrote.
It looks exactly the same as the other one I wrote,
Well,
right?
Colors. You're always going on about
Okay.
colors.
There we go. Oh, that makes me feel good and warm and fuzzy inside. Okay, there we go. Colors. Now it looks the same. But is it the same type of bond? No. So what we want to do is call attention to the fact that it's not the same type of bond, but we do want to keep this information of the negative and the positive. So what we will say is that oxygen is taking some of the electrons, but not all of the electrons. And if it doesn't take all of them, it can't be formally negative. But it could be starting to become negative. That starting to become, we'll add the little delta symbol. That's a partial charge. Why has this become important to us? That also applies out to the other system. Partially negative, partially positive. So we run into the same system. That purple interaction is the primary interaction up here. This one should be a little bit more clear, okay? Because if I'm going to stack these next to each other, and I say OH bond, now when I go through and show over this one, whoops, not that way, I would not space them so close to each other that it would appear to be a formal line. Why? Because if I put a formal line there, what happens to the octet on hydrogen? It's exceeded, and I can't do that, which means there is not a bond there. This one becomes a little bit significantly, or becomes significantly different from our ionic scenario, where it was kind of confusing, floating in a gray area. This black line that we're talking about is an actual sharing of electrons. This blue line over here is an actual sharing of electrons. There's still an attraction between the black hydrogen and the blue hydrogen. That attraction is there because the black hydrogen is partially positive and the blue hydrogen is partially negative. I have that attraction. Okay? That is significantly different than those solid lines. Does that make a little sense? Okay? What does this mean for us? Okay, well, what does that in turn come back to? Well, we should be able to overlay that back with what's going on over here. We could now call that a force. Is it the same force as over here?
No,
Why is it different?
because of the different bonds.
What makes it a different bond?
One's ionic and one's polar.
And I haven't officially pushed that polar part. Okay. We're calling this other one a covalent bond
Okay.
for the moment. Okay. The covalent bond is actually sharing electrons and the ionic was not. So we are going to get a different interaction. Okay? So that force should get called something different than that force, which now means I need to name them. How do I want to name them?
One stays the same, and then isn't the other one dipole?
Okay, we could call one that's staying the same, which I believe means you're calling that one an ionic force,
Yeah.
which I think is actually kind of a nice statement because that goes to referencing the confusion between an ionic bond and ionic force. They're ultimately the same thing, and it's very hard to differentiate them. But you'll sometimes hear people refer to the force part of ionic as electrostatic instead of ionic. What's happening over here? Okay, well, we need to come up with a name. I don't want to call it covalent or ionic or polar covalent because all of those are inherently bonds. I need a new name. Chemists are not creative. Okay, we've got a negative and a positive, which means we have two poles, a north and south end. So this is a dipole. What's the other molecule? A dipole. What kind of interaction do I get when I bring a dipole near a dipole? Dipole, dipole. It's literally in the creation of just defining the pieces that go into it. That interaction we'll call dipole, dipole. So they're different. Why does that matter? Why do I care that they're different? How much energy is it going to take me to break the dipole, dipole versus break the ionic force?
Less.
Why less?
Because the ionic one is the strongest.
Why is the ionic one stronger than the dipole, dipole?
Because it's sourced from ionic bonds.
You're dancing around the answer.
Okay.
What's creating that force?
Oh, that one is partial, and that one's not partial.
These being partial charges are not very strong positives and negatives. They aren't a very strong magnet. These ones being formally positive and negative are very strong magnets, which means the force created between those strong magnets is significantly higher than the force created between these ones, which means if I go through and create all things equal, it's going to require more energy to break that force than it will to break that force. What happens when I break that force? This was two molecules. What happens when I break the force connecting two molecules? What do I have when I've got two molecules connected? I have a solid. What happens when I break the force? I transition to a liquid. Okay? This one I would predict to be a solid more than this one because it has a stronger force. So if I understand something about the strength of those forces and where they're coming from, I can now start to predict the phases at a given steady state. That's pretty neat. Not only that, I can predict when the phases should transition. Okay? That transition is how much energy does it take to break that? Well, it takes less energy to break that than this one, which corresponds to a lower melting point or a lower boiling point to break the weaker force. So if I can identify the bond type and thereby identify the force, I can now make predictions about melting points and boiling points. That's pretty neat. Okay? This is why what you should be able to do is to look quickly at a molecule and say what bonds are present. Because once you know the bonds that are present, you can then have a conversation about what are the forces. Once you know the forces, you can then have a conversation about the phase transitions. So when we look at this let's go ahead and look at this one. What bonds do we see there?
Polar.
And
Covalent? Should I just say covalent?
okay, so now we could try and push through to defining these. Okay, I would argue right away it's very hard to see any bonds because we aren't looking at a Lewis structure. That's because what are you supposed to do as soon as you see that formula? Either draw it out or have drawn it in your head so that you know what it looks like. And if we draw it out, we should notice a couple things coming to play. What are those couple things? There's a highlight for one. There's a highlight for another.
The red one is ionic.
The red one is an ionic bond. How do you know that's an ionic bond?
Metal to non-metal.
Sodium is a metal. So if we've identified our elements and what they are very quickly, we can quickly assess what kind of intermolecular or what kind of bond is present. So the red one is ionic. We then have purple and green. Well, in all of those cases, purple and green, do we have any metals? No, they're all nonmetals. Okay? So aren't they all covalent?
Yes.
Yes. Is there a refinement that we could make on covalent?
Yes.
Yes. Why?
Based on how the electrons are shared.
This has to do with the electron sharing. Okay? And what we end up doing is further subdividing the covalent category into two primary sections. Nonpolar covalent, meaning they are 100% equally sharing electrons. And if they are 100% equally sharing electrons, okay, we do a carbon to carbon, and we'll color code it. Which of these interactions, purple or blue, is more valid?
It doesn't matter.
I don't know. There is no definition that would make it better because there is no partial charges being generated. Those are equally sharing of electrons. Because they're equally sharing electrons, there is no partial charge associated with it, which then pushes us to the next level. Okay? If it doesn't matter which one, let's just pick the top one. How strong do you think that interaction is?
Not very strong.
Not very strong at all. The only reason we're getting an interaction is because there's charges. If there's no charges, there's no interaction. There's no reason for the molecule to seek out and touch anything else because it has a very strong internal partnership. Kind of, sort of. So if we now go through and take a look at our system down here, we want to be able to differentiate our C to C from our, say, O to H. Because the O to H had a partial positive and a partial negative. That had a clear winner of interactions. Okay? So we need to think through and look at those bonds to decide those classifications. So we might go through and say, well, clearly the green one is different because it's bonded to oxygen. And since oxygen is the second most electronegative element, that oxygen is going to be carrying a very large partial negative, which then means that carbon will be very large partial positive. Cool. What about the carbon-to-carbon bond? Well, now they're nonpolar. They aren't, or they are sharing electrons perfectly evenly, which means we don't generate any large charges off of that. How about the carbon to hydrogen?
Same.
Aren't those different elements? That's not same to same anymore. Okay? And this is where that carbon to hydrogen bond has such a small difference in electronegativity. Okay? It's so small that we say it's effectively the same as sharing electrons. We've done this kind of thing before. What happened to atom size across a row?
Not much.
We said it wasn't enough of a change to say it changed at all. So we said across a row, they all stayed the same. We're doing the same thing here. Carbon to hydrogen has such a small difference in electronegativity that the charge imbalance is insignificant, which means all of those purple bonds generate zero charge. What does this mean for us? Well, now I want to say something about its melting point. Which of those interactions are ionic, are polar covalent, or are nonpolar covalent, are going to generate the strongest intermolecular force? The ionic, because it has those full-on charges of positive and negative. Which means if I'm going to take a first stab at what's going to dictate the melting point, it's going to be right there looking at that ionic bond. Because I got that ionic bond, that's going to dictate my melting point. Is the ionic bond strong or weak? Strong, which then means what should happen to my melting point? High or low? It should be much higher because I require more energy to break that interaction. So looking at this molecule, I might predict a high melting point. I'm not defining it. I'm just saying I predict a high melting point. You're being asked to now compare this molecule to this one. So what do we have to do? The exact same thing again. And we draw out the whole structure and we try and apply what's happening within it. And what do we see within this one? There is no ionic bond. Okay? Do we need to dig any further? No. The ionic bond was the stronger force of those two. The ionic bond is going to dictate my melting point. Since I want to know which one has the highest melting point, that one's the strongest force. That ionic compound is now the one with the higher melting point. Okay? In each of those scenarios, what we are doing is drawing out the molecule to understand the types of bonds present, and then saying when that molecule interacted with another molecule, what would that attractive force be? Neither of these cases are we actually breaking any bonds. All we're talking about is the theoretical forces that would be generated. What about the next one up?
I don't see any bonds.
Okay? So, cool, we're picking up, ionic bonds are the answer. We got to look for ionic bonds. Except what's the problem here? No ionic bonds. So we made it more challenging. Instead of going to the ionic bond, we had to now branch out and see what's happening within other scenarios. So if we quickly draw out our structure again, we could now go through and evaluate our structures to identify those types of bonds and hopefully then the forces. So what types of bonds do you see present within these? The purple, again, is our nonpolar covalent. The greens are going to be our polar covalent because we have those large differences in electronegativity. What types of forces are going to be generated from a polar covalent bond?
Moderately strong.
Fair.
Medium?
Okay. Not an ionic force, but a dipole-dipole force.
Oh.
Okay, so a slightly weaker force. So both of these compounds we would expect to have a lower melting point than that last set that we looked at. Okay, but we're not asked to compare it to the last set, we're asked to compare between these. So what we've got to do is look for that difference. Do we see a difference?
Yes.
Okay, what difference do you see?
Where the full bonds are.
Okay, where? Keep elaborating.
Well, one of them it's carbon to oxygen, oxygen to carbon. The other one's carbon to oxygen, oxygen to hydrogen.
Okay? So you could be referencing just the location of where the oxygen is could have an effect on it. There's another more important factor that comes into play before then.
There's a hydrogen bond.
And this becomes a weird statement. I see a bond between oxygen and hydrogen. When you say hydrogen bond, is that what you're referencing?
Yes.
No. Okay? You're not referencing that.
H bound to O.
Okay? That is a bond between oxygen and hydrogen. When you're saying hydrogen bonding, what are you referencing?
One of the types of forces.
It's the force that that hydrogen exerts on the oxygen in a separate molecule. It's still a polar covalent bond. Why would I call attention to this force being anything different than a dipole-dipole force?
It's special.
Why is it special?
It's stronger than dipole-dipole.
Why is it stronger than dipole-dipole?
I don't know.
Stop asking me why.
I don't know.
What is the difference between carbon and hydrogen?
Because of the drastic difference in electronegativity between atoms.
Hydrogen has a slightly lower electronegativity than carbon, which means the difference in electronegativity between the oxygen and the hydrogen is larger than the difference in electronegativity between the oxygen and the carbon. What does that mean? This is a smaller version of the ionic bond. What we're saying is that that hydrogen has a larger partial positive, that oxygen has a larger partial negative than in the other scenario, because the hydrogen has a lower electronegativity than carbon does. This creates a larger dipole so that the dipole-dipole interaction becomes stronger. How much stronger is it? Enough that what do we call it? Hydrogen bonding. We invent a new category for this specifically because that difference in electronegativity is enough to generate such a stronger force that we want to differentiate it from dipole-dipole. Okay? That's the existence of hydrogen bonding, which is challenging because when we say hydrogen bonding, what does it sound like we're talking about?
Hydrogen bond.
A bond. And we're not talking at all about a bond. Why did someone call it hydrogen bonding if it's not a bond? They were probably thinking that this is such an important interaction that I really want people to not forget about it, so I want to call it a bond so people evaluate it as importantly as a bond. Cool story, bro. That's not very helpful. You just confuse the shit out of everybody else that has to learn this information. Apologies. I didn't mean to say that. If you didn't hear it, don't worry about it. Don't rewind. Kind of, sort of?
Yeah.
So we need to know when we have hydrogen bonding as a potential force. Well, first and foremost, what did we have have hydrogen bonding? A dipole-dipole. After that, Jennifer, what did we need to have?
Either fluorine, oxygen, or nitrogen.
Close.
A polar bond.
So what we've said is we need a dipole-dipole and we need fluorine, oxygen, and nitrogen. So I need fluorine, oxygen, nitrogen, and a dipole-dipole, and I have hydrogen bonding. What's the name of the force?
Hydrogen.
Hydrogen bonding. Did you mention hydrogen at all yet? No, okay. What do we need to have hydrogen bonding? A dipole-dipole force and a hydrogen that is bonded to oxygen, nitrogen, or fluorine. Okay, so it's not just the presence of oxygen, nitrogen, and fluorine. Ta-da, presence of oxygen, yet no hydrogen bonding. I have to have the hydrogen bonded to oxygen, nitrogen, or fluorine. Okay, which means you need to know those three elements. If you've had enough of my jokes, you just remembered. Jennifer got it. Come on. If you had enough of my jokes,
You just sound Canadian.
nitrogen, oxygen, fluorine. Or perhaps you thought organic chemistry was just so much fun. You need say, oh God, that's probably appropriate. Okay? You need to remember those three are really important because you have to have the hydrogen bonded to one of those to get hydrogen bonding. Okay? What does that mean back to this question? The second molecule has a dipole-dipole force that is so strong because it also has the hydrogen bonded to oxygen that we generate hydrogen bonding as a force. This one only generates dipole-dipole. Which force is stronger? Hydrogen bonding. Which force or which compound has the higher melting point?
The one on the right.
The one on the right. Kinda, sorta? Think you got it? Yeah? Do number 2. I won't make you do number 1. Or if you really think you got it, you can do number 1. So hopefully what you're starting to pick up is a little bit of speed, being able to look fluidly at our structures and our formulas. That was partly what we were doing in Unit 1, was trying to pick up that kind of speed and formality so that you could quickly do interpretations of structures. And ideally what you see out of the gate is that you've got that oxygen sitting in the middle. That oxygen, if we draw out our structure, is now connected to those carbons on the sides. And I'm not going to draw all the hydrogens because I don't feel like it. If we looked at the other one, we're not going to have that same oxygen interaction. That oxygen is generating polar covalent bonds. Those polar covalent bonds lead to dipole-dipole forces. Those dipole-dipole forces are stronger than our very weak interactions. What's the interaction with this one? With just our covalent bonds? Generates which force? Our London dispersion. Cool, we've got that. Dipole-dipole being stronger than London dispersion. Therefore, the rightmost structure is the correct one. Good?
Oh, no, it's the first one.
You're thinking about the first one. Okay. So that takes us to our first one. And if we go through and look at the first one, what do we see?
The first one, well, A has 3 carbons and B has 6 carbons.
We're looking at non-polar covalent forces or non-polar covalent bonds in both cases. There really is no difference that says covalent, which then gets us to our London dispersion forces. It'd be like, well, if they both have London dispersion forces, which one could possibly have a higher melting point or boiling point? Okay. So what you might initially say is, it's the same, right? It's a decent conclusion. They're the same because they have the same intermolecular forces. Surface level, okay. You're all shaking your head at me, no. So cool. Why are they different?
The larger the molecule will be harder to break apart.
Why is the larger molecule going to generate stronger forces?
Because there's more interactions.
So I phrased it oddly. It doesn't generate stronger forces. It generates the exact same strength force, but what does it generate?
More forces.
More of those forces because there's more surface area for the molecule. So when we're looking at our phase transitions and some of our solubility things, okay, these physical changes, those physical changes are dictated first and foremost by the strength of the force, which is why it's very important to identify that. But then you will see secondary effects. Biggest secondary effect is just the size of the molecule. So you can get very large molecules having very high melting points, even though they have very weak forces. That's because they're large. There's enough mass behind them that they can generate more interactions per square unit, which requires more energy to break. Kind of, sort of? We feeling better with those? Okay. In that talking through it, what we were effectively doing is evaluating this chart. We start with the left half with our bonds. We identify what type of bond we've got. Okay? A covalent bond is a very strong bond. Okay? An ionic bond is a very weak bond. And that should immediately set off alarm bells. But for sodium chloride, that had an ionic bond. And when I looked at just methane, okay, any of those carbon-hydrogen structures, those had very strong bonds, but the phase transition was way different. Sodium chloride, with that very weak bond, has a melting point that is through the roof, 900 degrees Celsius. But if I move to something like methane, with these very strong bonds, its melting point is like negative 200 degrees. That doesn't make sense, Mike. What dictates phases?
Forces.
What force does a very strong covalent bond generate?
Oh, you mean that's not
A London dispersion force. An ionic bond, as a very weak bond, generates a very strong ionic force. The forces dictate the phases, not the bonds. Okay? So when we're looking about it and going, well, ionic bonds are weak and covalent bonds are strong, that doesn't make any sense. It doesn't make any sense because what you're using is your phase transitions to evaluate that, and those phase transitions are wrong. The phase transitions are based off of the forces. Okay? What does this mean for us as far as our chemical reactivity goes? If I look at covalent bonds, would I expect them to react?
Not really.
No. The only bonds that I would predict to react would be the polar ones. They're generating charges, and I want to stabilize those charges by partnering them up with something else. Covalent bonds do not run chemical reactions easily. Okay? So this helps me to classify now chemical reactions. When I look at a reaction, I can say, oh, I can ignore that part of the molecule because those are all covalent bonds. The only part I need to worry about is this part of the molecule because that's polar covalent or ionic. Yes? No, you're just thinking through it?
No, I'm just curious because we're not going to be dealing with metals a lot.
True, we don't deal with metals a lot, but we do deal with ionic substances. And the reason we deal with ionic substances has to do actually with this guy, our solubility, which is actually the lab happening today that you're not in. But that's okay. Okay, so what do we mean? So theoretically, we've got our phase transitions down. The vapor pressure, viscosity, all those I don't really care about. The ones that really stand out that are going to become useful are phase transitions, our solubility, and our reactivity. I would argue we've now covered phase transitions. That's now done. Okay? Those are the easiest form of this because it's a same substance. We just duplicate the same molecule again and again. Solubility and reactivity become a little bit more challenging because now it's not the exact same molecule again. I have to bring in a new molecule. And how does that new molecule now interact, okay, with that system? Okay, whoop. So our phase transitions, okay, boiling points to resist those phases is kind of what we all talked through. So do you think we're okay with melting points and boiling points?
Yeah.
Okay. Solubility is the ability for two substances to mix and form a homogeneous system. Okay? So if I go through and I take might be making guesses about ages or experiences. Ethanol. Everybody know what ethanol is?
Yeah.
Yeah, okay. And I take water. Right? We know what water is.
Yeah.
Do they mix? We're getting some no's, so we might have misjudged the ages limit. Guess what ethanol is and water? You mix them together and you have beer. Okay? If you scale up the alcohol concentration and reduce the water, you get vodka, you get whiskey, you get Everclear. Water and ethanol perfectly mix. 100% homogeneous. Right? What this is saying is that if we understand something about the intermolecular forces for those individual compounds, we could predict that they would mix. So, what's the structure for water?
H2O.
Officially, that's the formula, but that's okay. Close enough, right?
Draw it with my words.
If we looked at ethanol, which theoretically you guys should be able to do just from that name. Eth is two carbons, and they're all single bonds. The all is the alcohol.
Yep.
Okay? And if you aren't able to do that, that's kind of okay because we got a little bit of time before the next exam. I'm going to bet 2 weeks, just to give you a heads up. So it won't be next week, but I think it is going to be the following. I think week 9 makes sense. Okay? What are the forces that we would predict for water?
Hydrogen bonding.
Hydrogen bonding. What are the forces that we would predict for ethanol?
Hydrogen bonding and
Okay, cool. Hydrogen bonding and then
London dispersion.
London dispersion forces. Okay, officially you're missing one,
And
We also have that dipole, which I'm just going to do double D, LDF was the other one. Okay, that force, or that interaction is our dipole. We just said forces are our predominant predictor of everything. So if we had stronger forces in one case, that predicted the phase. When we talk about solubility, we can still take advantage of our forces. What is the strongest force in both these molecules? Are those interactions similar?
Yeah. Well,
Which means, should they mix?
yeah.
Yeah. And they do. Right? What happens if I make it propanol and I add another carbon? Does that change the amount of forces? Or the numbers of forces? Do I still get hydrogen bonding, dipole, and dispersion?
Yes.
Yes. Is it still soluble in water?
Yes.
Yes. How about I make it butanol?
So it's
I make it pentanol, hexanol, heptanol, octanol. You'd be like, all the same. It's all the same, Mike. Shut up. Stop it. They will all be soluble. Nope. Ooh, it all of a sudden changed. Why did it change?
because it's really big.
It's not just the raw strength of the force, but it's now also the relative amount of that force. As we start adding on more and more carbons, the relative contribution of our London dispersion force now starts to overcome the strength of the hydrogen bonding force, which means the predominant interaction we now see for this molecule isn't hydrogen bonding anymore, it's London dispersion, which means London dispersion versus hydrogen bonding, they don't want to interact. London dispersion doesn't want to interact with anything. Hydrogen bonding wants to pair up with charges. Okay? That reduces the interaction between them and it becomes insoluble. So when we're going through and balancing out our solubility, the first thing we kind of approach is this rule of thumb. It was actually the bottom, I thought it was actually already there. Is like forces dissolve like forces. You probably heard like dissolves like, okay? Which I hate as a reference because it's not telling you what the thing is. It's forces, okay? So this is why when we look at our molecules, we want to identify the force present. If we know the force, we can then predict something about its solubility in other systems and all that other stuff. Does it get complicated? Yeah, okay? The larger or the more amounts of those forces can change the solubility. This is why it's a rule of thumb, not a perfect system. How would we know for certain? You test it, right? And in most scenarios, when we're talking about solubility, what we do is we go into the lab, we want something to dissolve something else, we test it. Oh, that didn't work, so we try a different thing, right? But it's not just a shotgun approach of let's just try everything. It's trying to match those forces first. The closer we get with those forces, we can whittle down some of the tests that don't make sense to test. Kind of, sort of? Okay. So when we talk through our solubility, what we're trying to do is find those similar forces, and then, actually, how far do I take it? We take a slight break off of it. What? That's where I put it? Oh, this slide is misplaced. This slide should have been placed before our solubility. What are we talking about here?
Phase changes.
This is our phase changes. So solid sodium hydroxide, what's our force? We're a metal, so we're ionic. So that would predict a solid. Liquid water, why is it a liquid? Because it has hydrogen bonding. It's a weaker force than the ionic one. Okay, so it's trying to pick examples that target that, and it was just misplaced. I apologize. What we move into now with our solubility is what we do with it. Okay, solubility isn't just do things mix. What we want to recognize with the point of solubility is trying to set something up. Okay, and ultimately what we're trying to set up is our chemical reactions. When we run a chemical reaction, we want our two reactants to mix and talk to each other, to interact. Okay? The easiest way to get them to interact is if they're in the same phase. Best phase to run it in? Gas phase. Because in the gas phase, they aren't talking to anything else. They're just free-floating molecules, and if they impact each other, we get a chemical reaction. Gas phase reactions are classically very difficult in organic chemistry because we have to add enough energy so that it transitions to the gas phase. What happens when you heat up an organic substance? We can be real nice. Take a block of wood and put a match to it. What happens? It burns. It reacts with oxygen and turns into something else. We get a different chemical reaction. So trying to get things into the gas phase is not particularly easy in and of itself. Add to that gas phase reactions are particularly dangerous because what does the gas do?
It freely spreads out.
It fills whatever the container is. So that means if we ran a gas phase reaction in here, like I tried to run it in a beaker, the whole room is going to fill with that gas, and that could be very, very dangerous. Okay? If we put it in a sealed container and we're reacting a gas, if the gas changes its volume in a sealed container, I've made
Shattered glass.
a bomb.
Oh.
Yeah. Okay? And so we tend to not deal with gas phase reactions much in an undergraduate environment or really at any environment because you have all sorts of secondary safety considerations that we've got to worry about. Okay? Which then means we're dealing with our liquid and solid systems. Liquids and solids actually don't work very well either as a mixed system because the only place the liquid can interact with the solid is on the surface of the solid. Everything is trapped underneath, which then means the liquid makes the most sense. But now liquids would have to mix with each other, so we're now starting to talk about solubility. But that would also now limit us to only liquids interacting. Sodium hydroxide is a solid. Okay? So how can we ensure that our pure liquids and our pure solids can interact with each other? Introduce a third material. That third material would be your solvent. You used a solvent in all of your chemical reactions that you ran in Gen Chem. What was that solvent? Water. We tend to not use water in OChem because it's not organic. Okay? And other reasons which we can look at potentially later in the semester. Okay? But as a solvent, water is very reactive and we tend to avoid it. So that means we need to address other solvents that could potentially come into play. Those solvents are now going to be categorized based off their intermolecular forces. And the two most common definitions that you'll hear floated out there are polar and nonpolar, which officially I hate as terms. Because if you ask someone to define polar, they can't. They literally can't. Okay? Or, even better, they create a definition that you can very quickly challenge and break when they define it as polar. Okay? And the issue becomes that polar and nonpolar are these very tenuous terms that don't really work very well. So when we're talking about classifying as polar and nonpolar, really what we're talking about is the strength of the intermolecular force. If that intermolecular force is strong, we would start to push towards it being polar. If it is weak, we would start to push towards calling it nonpolar. So they're broad kind of categories. If we looked at water we might classify as what? Polar, because?
Just
Hydrogen bonding,
unequal sharing of electrons.
the unequal sharing of electrons, because we have a polar covalent bond within that. That polar covalent bond gives us a large, started to draw the wrong sign, negative and a large partial positive. If we move to something like acetone, you're not responsible for knowing acetone, is this for the record? Mainly because it's not a nomenclature name. You are technically responsible for being able to predict the name for this compound. Let's do a quick naming check. How many carbons? 3, so we call it. How many is 3 carbons? Prop. Okay. Those carbons, for the most part, excluding our carbonyl, are single bonds, so we'll call it propan. Okay. What is our functional group? It's a carbonyl situated between 2 other carbons, which makes it a ketone. How do we name our ketones? We change the ending to -one. This could be called propanone. Where is the ketone located?
Second carbon.
The second carbon. This gets called
2
to propanone. Okay? That, as a name, you should be able to go through and do. Acetone, I don't expect you to figure out. Okay? So, what do we think for this compound? Polar or non-polar? Why polar?
The carbon to the oxygen.
That carbon to oxygen bond is generating a large difference in electronegativity. We're getting a fairly large negative and a fairly large positive. So we could classify this as polar. Okay, kind of makes sense? If we shifted to, let's say, benzene with lots of abbreviations, and that line angle drawing, all of those points are carbons. Each of those carbons has a satisfied octet. Our formula becomes C6H6.
Not
This is now classified as nonpolar because all of those bonds are nonpolar covalent. That sets us up in that nonpolar category. Okay, so we've got a way to kind of differentiate these solvents and come up with those classifications. Why would I choose one solvent versus another? Okay, well, if I want to dissolve sodium hydroxide, which solvent should I use to dissolve sodium hydroxide? Why should I use a polar one?
because they're similar.
How are they similar? You just aren't giving me enough to work with.
That slide that said, what was it, like solubility?
Like what?
I need to-
Like forces dissolve like forces. So you're saying they're similar. What are their forces?
Dipole, and ionic.
And ionic. Okay. So this is an ionic force. Okay. And up here, you might be referencing that as eventually officially leading later
Yeah.
to our hydrogen bonding. Okay. And actually, I'm going to scratch that because what did you say?
I just said dipole.
Dipole. So you said water, right?
Yeah.
Doesn't acetone also generate that dipole?
Yeah.
So why water?
I'll go left to right.
Why water and not acetone?
Smaller.
As a hint, I erased something. Why is the hydrogen bonding the more relevant force to address?
It's stronger.
It's a stronger force. And if we look at that rainbow chart, ionics up at the top, followed by hydrogen bonding. Dipole is lower than it. And if we're talking about similar forces, we want things closest to each other. That ionic force is most similar to our hydrogen bonding. That would suggest that's a better interaction. Okay? Which means that water one as polar and our acetone as polar didn't do the same thing. Which means our definition of polar and nonpolar has a gap in it, which means we should introduce yet another terminology with it. That other terminology, is now moving into the system of protic versus aprotic. What does protic sound like? What is prot? Fair. But no, that's just pro and probiotic. So that's probio, but this is prot. Give me the T at least. What did you say? Okay, proton. But we don't talk about protons reacting necessarily. What is our proton? When we say proton in
Positive.
positive what? What thing is positive? It's a hard question.
The partial charge? I don't know.
This is considered a proton in organic chemistry. You're like, isn't that a hydrogen? It is a hydrogen, but what happens when I bond that hydrogen to oxygen? What happens to the electrons in that bond?
It's unequally shared.
They're unequally shared. They effectively all go to where?
The oxygen.
The oxygen, which means what is identified within that purple box?
You left for just one proton.
I only have a single proton left over. So when we're talking about protic, we are referencing proton, but we're referencing proton in a very strange sense. We're referencing it as the hydrogen ion. or rather a positive hydrogen. So our protic is saying H plus with the potential for that being a positive, partial positive. Okay, and in fact, most scenarios it's partially positive. So if we go back to our water, is this one protic?
Yeah.
Yeah, because we have a large difference in electronegativity between our oxygen and our hydrogen. There's our protic part. If we went back to our acetone, which I'm not going to draw all the way out, we do have that large difference. There's our polar. But do we have a hydrogen?
No.
Really? Aren't those all hydrogens?
Not right in there. No, next to the O.
Why is it relevant where it's located? It's not just that it's a hydrogen, it's that it is
A positive charge.
a positively charged hydrogen. For it to become positively charged, what must the hydrogen be bonded to?
Something that'll take its electron.
Something that would take its electrons. More specific.
Oxygen, fluorine.
Oxygen, nitrogen, or fluorine. Protic is specifically referencing our hydrogen bonding solvents. So if we look at a solvent and we say, oh, it's got a hydrogen bonded oxygen, nitrogen, or fluorine, that's now a protic solvent because it has a hydrogen bonded to nitrogen, oxygen, or fluorine. So our protic is really just saying hydrogen bonding. Okay? Which now sets us up. We've got a whole bunch of extra terms that could float out of this. We could get a solvent that is polar and protic, so we could call this polar protic. Okay? We have a solvent that is polar and aprotic, so we could call it polar aprotic. Could we have a solvent, never mind. Could we have a solvent that is non-polar aprotic?
Yeah. Just like C to H.
Yeah, the C to H. That was non-polar aprotic. Could we have a solvent that was non-polar protic?
No,
Why not?
because it would automatically be polar if there was hydrogen bonding.
As soon as you bring in hydrogen bonding, that generates a polar force, which means we only get three categories: polar protic, polar aprotic, and non-polar aprotic. Okay? That's still a mouthful of three categories for our solvent terminology, and I would argue we could adjust this down based off of exactly what you just said. If it was protic, it had to be polar. Do I need to say polar protic?
No.
Nope. All I need to say is protic. Okay? If it was non-polar, could it be anything other than aprotic?
No.
Nope, which means
Just
I can get away with just saying non-polar. The middle one becomes a little bit questionable. Okay? I would argue you could get away with just saying polar because we've excluded polar being labeled as protic. Okay? And the aprotic we already excluded over there. So I would say you could probably call this one just polar. Most people will still call the middle one polar aprotic. Kind of, sort of?
yeah.
Do you have those definitions now down roughly?
So pretty much we're just calling aprotic not hydrogen bonding.
Yes.
Okay.
Aprotic is not hydrogen bonding. I'm going to break that in a second, but yes.
Well, that's whatever.
Okay. Well, it's an okay thing to write, and we just have to address why it's potentially problematic here in a second. We good? This is DMSO. Dimethyl, so 2 carbons, 1, 2, sulfoxide, sulfur with the double bond to oxygen. Classify it. Is it protic? Is it polar?
Polar
Is it non-polar? And before you forget, remember there are hydrogens out there on those carbons. You think you got it classified? Not Devin. Anybody else? What's the solvent classification? before you call me out for color coding. Is this solvent protic, polar, or nonpolar? You said you had all the definitions. Is there any answer you think it is not? I was hoping that was an easier answer. Okay, protic. It is not protic. We don't have a hydrogen bonded to oxygen, nitrogen, fluorine. Just because we have hydrogens does not make it protic. The hydrogens must be bonded to oxygen, nitrogen, and fluorine. So now between polar and nonpolar, what's our difference between polar and nonpolar? It's not really sharing of electrons because polar and nonpolar are ultimately both covalent bonds, so they're both talking about some level of sharing of electrons. How do you have a nonpolar bond? So this goes back to that video on intermolecular forces. We need to be able to identify quickly the types of bonds present within our molecules so that we can make these kind of leaps of calculations. If we don't have the ability to classify those types of bonds, we're kind of dead in the water. So is there an ionic bond? No, because we don't have a metal. Is it a covalent bond? Yes, there are some covalent bonds. Which of those bonds are covalent? Carbon to hydrogen, yep. Any of the other bonds covalent? What was our definition for covalent? Same to same and carbon to hydrogen. The carbon to hydrogen are now just our raw nonpolar covalent. Okay. Do we have anything that's same to same? Nope. Which means the rest of the bonds are polar covalent. If they are polar covalent, can we possibly be nonpolar? Nope, which means it's polar, officially polar aprotic, but I didn't really want to draw that ugly looking box. Kind of makes sense? Okay. Because Devin asked a question, let's go ahead and see if I can't break something. I now look at a mixture. This is a mixture of DMSO and water. In this mixture, we're going to see this interaction, shown in blue dash. Name that force.
Hydrogen bond.
This should be an interesting label, because if we go through and look at it, between those two molecules, those are two very different molecules, but we're being asked to identify the interaction between them. In identifying that interaction, okay, do we have what types of bonds are present? So the first thing we should do would be identify the bond present with that oxygen. What bond do we have going to that oxygen?
Polar.
That is going to be a polar covalent bond because it is not same to same, it is not carbon to hydrogen, and it is not a metal to a nonmetal, which makes it a polar bond. Okay? What bond do we have between the hydrogen and the oxygen? Polar. When we bring two polar bonds near each other, what type of force do we generate? We generate a dipole-dipole. Before we move to calling that or settling it dipole-dipole, what do we have to evaluate? After we've identified a dipole-dipole force, we should be looking for one more special thing, which gets the answer that you were mouthing.
Whether there's hydrogen to oxygen.
Is there a hydrogen bonded to oxygen, nitrogen, or fluorine? Yes, which means that's hydrogen bonding. Does DMSO have any hydrogen bonding? No. But if I mix DMSO with something else, could that resulting mixture have hydrogen bonding? Yes. So we have to be careful when looking at hydrogen bonding to make sure that we're answering the question that's being asked. Okay? Are we looking at a potential for a mixture, or are we looking for just that same compound? Okay? Kind of make sense?
Yeah.
With that, we're done.